Welcome. I'm Rich Wargo, producer for Science Horizons. I'll be your correspondent as we follow the people and the stories at the forefront of discovery, exploring where science is and where it is going. Tonight on Science Horizons, we take a look at a novel method to make the intangible truly tangible with computer models, and at two programs which enrich science education at different levels. But first on Science Horizons, how do infants see? Some of what we know is based on preconceptions, and psychologist Karen Dobkins is working to better understand how our little bundles of joy develop their view of the world. Professor Dobkins, thank you very much for joining us this evening. Your lab concerns many areas of vision research. Could you briefly describe the breadth of different investigations that go on here?
Okay, the lab studies visual perception, and we try to understand visual perception in terms of underlying neural mechanisms. Now, we focus particularly on color processing and motion processing. That is, how do we discern different colors in our world, and how do we know which way things moved? And we attack this problem using three different approaches. First of all, we study visual perception in adult subjects, and what this entails is having our adult subjects look at patterns that appear on a TV screen, and we ask them to report what they see. And we design our experiments in such a way that we can understand what must be happening in the brain in order to underlie the perception that they see. The second thing that we study is visual perception in developing human infants. And here what we're interested in is tracking the development of visual perception and trying to understand what neural mechanisms in the brain are constraining visual development in the infant. And the third thing that we study is visual perception in deaf individuals. And here what we're interested in is whether visual perception in the deaf differs from that of hearing subjects. And in particular, what we're interested in is whether an altered visual environment or sensory environment can alter the way the brain develops.
It's interesting that you are a neuroscientist by training. I mean, prior to this, you were involved with the cellular and the biological mechanisms of understanding how neurons and the brain works. And you're in the Department of Psychology. Can you help us understand the confluence of neuroscience and neurobiology and psychology and how that's relevant and important to these investigations?
Sure. So let's say you're interested in visual development. If you're a neuroscientist, you could be in a neuroscience department and study a very important question about visual development. That is, namely, how do neurons during in utero development know where to go in the brain? It's this amazing problem. Trillions of neurons have to find their target in the brain, and how does that happen? And there are people who study that. It's a very important question. But if you're interested in psychological issues like mental processes and behavior, like I am, then you might want to take your neuroscience to a psychology department and ask the question of how these developing neural mechanisms constrain visual perception in the infant. In other words, tie the two together. Look at the neural development, but then look at the consequences of the neural development.
In doing vision research, especially in infants, we can't very well go right into the cells and see what they're doing. How do you approach investigating visual perception and the processes that go on in your subjects?
All right, let me give you a concrete example. So again, when we design an experiment, we always do so with some prediction about what areas in the brain must be underlying a certain perception or the development of a certain perception. It's known from neurobiological experiments that the part of the brain that allows you to see red-green is different from the part of the brain that allows you to see black-white. If you want to look at the relative development of these two brain areas, you can find out in an infant the relative rates of perceptual development for red-green versus black-white or black-yellow stimuli. And so what we would do in our experiment is bring infants in at different ages and look at their sensitivity, how well they can see red-green versus black-white, and compare that to the relative sensitivity for red-green and black-white in an adult. And that way we can track the development of these brain areas.
Initiatives to increase our understanding of early development in humans are receiving greater support, and there's quite a bit of interest in this area. Help us understand what is going on in terms of visual development in this period in a human's life.
First of all, on a grander scale, in the first year or two of human life, there is an overabundance of connections in the brain. And what happens during the first 2 years of life is that there's a lot of reforming of synapses. There are many connections that were redundant that are then pruned away. All of this leads to the adult-like pattern of connectivity in the brain. In terms of vision, we do know a lot about what's happening in the visual system within the first year or two of human life. And as an example, a good concrete example is that right at the level of the eye, in the back of the eye, there's some neural tissue referred to as the retina. And part of the retina consists of these cells called photoreceptors, and these are these cells that actually capture light and signal to the rest of the brain that there's something out there. There are two things that make the infant retina very immature. First of all, their photoreceptors, the morphology of their photoreceptors is very immature. Typically, in an adult, a photoreceptor has a long process, whereas in an infant, that process, instead of being long and thin, is kind of short and squat. This short and squat nature of their photoreceptors make them very inefficient at capturing light. So that's the first thing that makes their vision immature. The second thing that makes their vision immature right at the level of the eye, the retina, is that adults have something called a fovea. That is a portion of the retina where the photoreceptors are particularly densely packed. That's what we use to see fine detail in the world. Infants don't have a fovea. They don't have a densely packed area of photoreceptors. Instead, they have a more homogeneous distribution of photoreceptors, and it takes almost 3 to 4 years in order for those photoreceptors to migrate towards the center of the eye and form the fovea.
There's obviously a lot of interest among parents about the development of their children. And I brought some things here that are ubiquitous with parenting. What have you found about infant vision, especially about this homogeneous nature of the cells in the retina and how they affect what an infant sees?
One of the experiments that we have conducted has to do with the development of red-green versus black-white vision. And I'll tell you that one of the questions that's been out there in the infant literature for a long time is, how well do babies see color? And the thought that was out there for a long time, the kind of the dogma that was out there for a long time, was that infants don't see colors very well. To dispel that myth, it turns out that it's not that infants don't see colors very well, they don't see anything very well. And what you find is that if you equate red-green stimuli with black-white stimuli in terms of how much contrast they're producing in the photoreceptors, then you find out that infants see both types, that is red-green and black-white, approximately equally well. So for example, we like to buy things that are pink and blue for our infants, but this is an example of a very low contrast color situation. The pink and blue are pastel, and they don't create as much contrast in the eye as something would that was more, let's say, this green versus this yellow.
So help us understand what our little bundles of joy are seeing, how they're perceiving these things. There are a lot of these things around, and probably every household who has a young infant in it has one of these. How do they see this compared to how we see this, and how do they see colors compared to this?
Right. Okay, so first of all, this is a very good stimulus for infants because it's black and white and it's high contrast. The black is fully black and the white is fully white. An infant looking at this would see something different from what we see. First of all, the black and white would not be as different from each other as they are here. It would look more like a dark gray and a light gray region. And secondly, they wouldn't see these nice sharp contours between the black and white. They would see fuzzy contours. So in other words, rather than seeing a sharp contour, black, high contrast black-white stimulus, they would see a fuzzy, degraded, dark gray, light gray stimulus.
What I'm understanding is that if we had a very bright red and a bright green, or a bright yellow and a bright blue next to each other, they would see it comparably as they see the black and white. Is that true? Absolutely.
They would see a lower contrast red-green than we see, and there would be fuzziness between the borders of the red and the green, although we would see a sharp edge.
You have some examples here of what we mean by high contrast colors.
So this is about as saturated red as you can get, and this is also a very saturated green. You put these next to each other, and you have a high color contrast. This is something even a 1-month-old would be able to see.
And let's go back into the biology of the photoreceptors and perception. What is functioning here that's making babies see
This degraded image.
This degraded image, yeah.
Again, it largely has to do with the photoreceptors and their inability to capture light. And that would explain why they see a lower contrast stimulus than we see. The reason that they tend to see fuzzy edges has more to do with the fact that they don't have a fovea. You'll notice yourself if you look at things without your fovea. In other words, if I look at you, but I try to pay attention to something out of my periphery where the photoreceptors are less dense, it's fuzzy. And that's what an infant sees.
How was the experiment conducted that led to this information about the perception of color and contrast?
So how do we get this information from infants who can't talk to us and can't tell us what they see? Well, we use a technique that's referred to as forced choice preferential looking, which you might find interesting, was developed by my postdoc mentor, Davida Teller, up at University of Washington. And this technique relies on a very simple principle, and that is that infants will preferentially stare at a pattern stimulus on one side of the screen as opposed to a blank, boring field on the opposite side of the screen. Now, what we do is we hold an infant up to a video monitor, a TV screen, and the infant can see what's on the TV screen, but the adult experimenter cannot see what's on the screen because there's this piece of cardboard blocking her view. What the adult experimenter does see is the baby's face projected on a camera monitor above, because there's a camera focused on the baby's face. Now, on each trial, a stimulus appears on the left or the right side of the screen. The adult experimenter's job is to guess, based on the baby's gazing behavior, which side of the screen contains the stimulus. If the stimulus comes up on the left, and it's a stimulus that the infant can see, the infant will tend to look to the left. The adult experimenter will guess that the stimulus was on the left, and the adult experimenter will be correct.
Start. Left. Start. Right. Start. Left. Start. Left.
We vary the contrast of the stimulus over trials because we're trying to determine the contrast level that the infant can just see. Now, when we do this experiment in the black-white or the black-yellow versus the red-green domain, what we're doing across trials is presenting both red-green and yellow-black stimuli, varying their contrast to get what we call a contrast threshold for both types of stimuli.
Now, while you found that our color perception and our contrast perception in infants is not as well developed as when we're adults, you did find something in your research about our early vision that is quite well developed. What is that?
Motion perception. A good example of that is that we know that babies soon after birth are able to track moving objects. You can just watch their eyes and see that they will follow something as it moves. So we know that there's something in the infant's head that knows about the direction of motion because they can track. We have found evidence in our lab that babies at the age of 3 months have motion processing capabilities that are very adult-like. This makes some sense from an ecological point of view because one of the first things that you need to learn when you come into the world is how to move out of the way of things that are coming towards you or to move towards something you're trying to catch. So for example, if you're prey and a predator's coming at you, you have to know which way that the predator's coming so you can run the other way. So it would be very important for these kind of motion mechanisms to be in place early on in development for survival.
That leads me to 2 questions here. It seems that the ability to recognize mom, which is food, would be quite important. And to me, it seems like our faces or our bodies, either primates or humans, don't represent that kind of high contrast that's easy for the young visual system to perceive. How soon does that develop, or is it even something that has to do with perception, visual perception?
Well, that's a very important question because the other thing that is very much needed by an infant as soon as they're born is the ability to recognize mother. But it turns out that you don't need vision to recognize mother. There have been studies that show that infants can smell their own mother and recognize their own mother by smell or by voice very early within the first week of development. So they don't really need to see mom to recognize mom.
The other question I had was, you say that our motion perception is well developed, and it would seem that this ability to perceive things sharply would work into that or be important in that. Is that true, or how is motion perception being dealt with this not well developed set of photoreceptors and fovea, et cetera?
Well, if you think about it, when I need to know that something is coming at me from over here, it can be a blob, it can be blurry, it doesn't really matter. I just need to know which way it's coming from. I don't need to know its color, I don't need to know about its edges, I just need to know its direction because I'm going to head the other direction. So really those are independent processes.
We've talked about color and contrast perception and motion, so parents are now thinking bright toys, black and white toys, things that move.
They're all good. I would highly recommend high contrast black-white, high contrast red-green, and moving stimuli. The animal literature has shown us that early sensory input, visual input, can absolutely shape visual perception and visual processing in the brain. And although these studies have not been conducted in human infants, there is no reason to believe that the same thing wouldn't hold true in human infants. That is to say that if you provide a lot of visual stimulation for your infant, there is reason to believe that their visual system will develop more quickly than had you not done so. However, it's not clear that that would be better. It's just probably the case that things would move along faster.
It would be my guess that from what you found about contrast and color, that one of the things you may want to investigate, you might be interested in, is motion and motion perception. Is that one of your future areas of investigation, or what are your future areas? What are your interests, and where are you leading now?
Well, there's still a lot to be done just in the question of color development and in the question of motion development. Specifically, one of the questions that we've had has to do with whether, when infants do see color stimuli like these, whether what they're picking up on is simply that there's a difference in color between these two things, or whether they really have color perception as we know it. In other words, does this lead to a percept of green and this a percept of red? All we know right now, really, is that infants can see that the red and green are different from each other, but what they experience in their head is still somewhat unknown, and that is one of the current projects in the laboratory.
Do you hope or intend that this area of your investigation would have applicability in dysfunction, in being able to predict or treat dysfunction?
Absolutely. We are not currently conducting experiments that have medical relevance. However, it's absolutely the case that before you can understand abnormal development, you have to scope out normal development, and that's what we're currently doing in our lab.
What are some of the key mileposts in our understanding of human visual perception? What are some important things that have happened, and where do you think we are now, and where are we going? What are the most important, the driving questions at this point?
In the last 40 years, our knowledge about infant visual development has increased substantially. Just from studies like those conducted in our laboratory, we know that visual perception develops over the first year quite a bit. We also know, based on the neurobiology, that there are many connections being formed and others being pruned away, and synapses being formed and taken away within the first year of life. We also know from animal literature, these are very important experiments, that during development there's something called a critical period. This is a period in which sensory input can influence the development of the brain. So we know from animal studies that the brain can alter itself in response to sensory input, but only during a critical period during development. And this had very important implications for the medical field. And that is because originally when children were born, when infants were born with what's called amblyopia, where one eye is not functioning correctly, and we don't exactly know why that is. Sometimes this can look like a lazy eye, or the eye might look fine, but it's just not processing things properly. Doctors used to say, well, let's do some corrective surgery to help that child, but let's wait till they're older and they can handle the surgery better. Now we know from the results of animal studies showing this critical period during development that if you're going to affect and change development of the brain, potentially correcting something like this amblyopia, that you need to do it during the critical period, that the surgery has to happen at a time when the brain will be responsive to the change that you make. So now they're typically conducting this kind of surgery for amblyopia within the first year of life, and it has made remarkable steps in the quality of vision for these children.
Thank you very much for being with us this evening. It was very informative, and we look forward to seeing what you discover in the future.
You're welcome. Thank you.
If you and your child are interested in participating in infant vision studies, please call the UCSD Infant Vision Lab at 822-0642. Next on Science Horizons, computers help reveal the world through modeling, and Mike Bailey of the San Diego Supercomputer Center has developed a method which really puts researchers in touch with things they could never hope to see.
Every field of science and engineering does some kind of simulation. The problem is everybody's trying to understand something. They're trying to understand something that exists, but exists in a form they can't see. Things that are too small, too large, happen too fast, happen too slow. They want to understand that. A lot of times people are trying to understand something that hasn't happened yet. They're trying to simulate something. If this happens, what will be the result? So pretty much every field of engineering and every field of science, medicine, biology, chemistry, physics, oceanography, astronomy, all the engineerings, mechanical, chemical, civil, electrical, everybody is simulating something. They're trying to understand something that they can't see or doesn't yet exist. Certainly the idea of drawing things to represent scientific information has been around for centuries. Certainly in the Renaissance period, people got very much into realism, like Leonardo da Vinci drawing pictures of human anatomy. Over time, as people were interested in more and more accuracy, the hand-drawn sketches were no longer adequate. And so as people were now trying to understand things to much more detail, computer simulation came into play, and then, of course, then computers were built that could draw things. Well, computer graphics just kind of escalated from there. It got faster. In the 1960s, it moved to monitors so that you could see it on a screen in front of you and not have to wait for something to come out on paper. The 1970s really introduced color to computer graphics. The middle to late 70s and early 80s really introduced fast three-dimensional hardware, so you could take objects and rotate them on the screen and run them through an animation sequence very quickly. The early 1980s also was the birth of the workstations. Instead of having massive computers that lots of people shared, you could now get something that is either a small number of people shared or you'd put one on your own desk. And so the idea back in the 50s is still exactly the same. Take data, draw something that I can understand. We've just gotten a whole lot more sophisticated about how we do it. One of the things we do here at the Supercomputer Center is run a machine called a laminated object manufacturing machine that knows how to build three-dimensional models. There does seem to be something about them that makes them supply a certain amount of information you don't get on the graphics screen. One of the things we know is for certain is true, is you get a better lighting model. That is a real object, the light's falling as light really falls, whereas on a computer screen we have idealized equations about how light works, and those equations were really designed to be fast, more so than to be realistic. For instance, shadows. When you hold one of these physical models in your hand, shadows fall across the face. And ever since we were newborns, shadows have always given us clues as to the depth and three-dimensionality of the world around us. Here you get them, and as you rotate this object, the shadows do what they're supposed to do. Whereas on the graphics screen, you can't rotate an object and get the correct shadows. We also suspect that there's a certain amount of focus. It's a perceptual thing called accommodation. When you look at the world around you, your eye, your lens is constantly changing its focal length to keep things in focus. And when you look at a computer screen, it's a flat screen. Whereas we suspect when you look at these, the fact that your eye is constantly changing focus actually gives you some clues to it. Now the other thing that of course we know is true is once you can put it in your hand, you can now start pinching it, feeling it, and you get a lot of clues to the shape. Again, as a child, what did you do? You always picked things up, played with them in your hands. Well, you probably put them in your mouth too, but we don't do that here. But just pinching it gives you a sense of how big it is in the middle, and you can't do that with a graphics screen. And then if you get two objects that are meant to interact in the same space with each other, and this is a great example, you can start bumping them together and see how they fit. This is part of the black beetle virus, which is some collaboration we did with Dr. Jack Johnson at Scripps Research. And they were interested in understanding how these things dock. And by playing with this, they found there's a pin here and a hole there and some ledges that interlock. And by doing this, you can exactly understand what goes on. And notice how tight that is. As I twist it, it doesn't come out. By doing this, you get a lot of information about the three-dimensionality of these two parts that you can't do on the graphics screen. That is, you bring them close to each other on the graphics screen, even when they start to overlap, you're not exactly sure that they've done that. The machine is called a laminated object manufacturing machine. It's made by a company called Helicis. What the machine wants is a list of three-dimensional triangles. Each triangle is defined by an XYZ coordinate at each of the three vertices. And so anything you can put in that form, we can manufacture. Now, when somebody comes up with their triangle file, they can get it to us in a number of ways. The way that seems to be most common is across the internet. On our web page, there's a way you can submit the triangle file right through the web page. Once it gets over here, sometimes we have to do some translation on it. Sometimes we have to, well, we always look at the geometry, and we have a program that will check for flaws in the geometry and possibly correct them if it finds them, and also then put it in the correct format to go onto the machine. And after that, we transfer it into the internal computer on the manufacturing machine, and it builds things up a layer at a time out of paper. Uses a special kind of paper. Actually, it seems like ordinary paper, but it's got a layer of glue on the underside, and this is heat-activated glue. So this is on a big roll inside the machine, and when it wants to add another layer to what it's building, it wheels a new section of paper into place. A hot roller comes out, it's heated to around 400 degrees Fahrenheit, and goes over the paper, melting the glue and laminating it to the layer underneath. Then a laser comes out and cuts out the cross-section of the part at that level. And you just do this over and over and over again until you have a part. Now, the paper's about 4/1000ths of an inch thick, so it's about 250 layers per inch. So for instance, something like this that's about 4 inches tall would be over 1,000 layers of paper. So that's why it's not a fast interactive process. But the good news is because it's not a subtractive manufacturing operation, we don't have to worry about getting drill bits, milling machine bits, down inside all these grooves and crevices. And that's one of the things that really helps us. When the part comes off the machine, it looks like a block, it's a brick. The reason is that when it cuts out the outline at each layer, it doesn't remove the scrap. What it does is it cross-hatches the scrap so that we can pluck it out later. When you take it all apart on the table, all the scrap starts falling out. Sometimes some of the scrap sticks to the part or gets down in some of the crevices, and then we have little dental tool looking things that go down in there and let us scoop it out. After that, you've got a finished part. It's kind of a fun process. It's sort of like opening a Cracker Jack box and there's a prize inside, and here we're opening up a wooden brick and there's a 3D shape inside. This terrain map of the United States is a really interesting example of what the machine will do. The whole thing's been vertically exaggerated, I think by about a factor of 60. The reason is basically the Earth is flat. And think of the United States. The United States is 3,000 miles across. The highest mountain in the mainland United States is about 3 miles. That's 1/10 of 1% of the width. So if you build it exactly to scale, it'll look really flat with maybe a little dimple or a little pimple here and there representing the mountains. And so you don't really get to see the mountains, the slopes, and so on. So we played around with the height exaggeration some. It's not good to do too much. It just looks weird. But we wanted enough where we could see the Rockies and the Appalachians and the Ozarks and so on. Now, one of the things that Dr. Gage studies was kind of interesting are these little gullies up here. Is over geologic time, those gullies have been created, and you can imagine if they show up this clearly on this kind of map, they're really huge, like 100 miles across. Well, this gully right here is where the Red River has ended up now. That's one of the reasons it floods, is because it's so flat in there, it's real easy to get over the banks. This gully over here is where the Missouri River has ended up. Again, note this all happened, of course, over geologic time. Notice you don't really see a similar gully like that for the Mississippi. We think of the Mississippi as being a huge, mighty river, but in fact, in geologic time, these forces have been far more significant, which is something that's just not obvious on a normal map. Well, this was actually a student project. One of those students who helps me run the place is Drew Clark, who's now a grad student here, but he took a design class last spring and they had to do a final project, so he designed this gear system on a CAD system and then manufactured it here. And so that's perfect, I think, is get this in the student environment. Students get experience going from design to prototype manufacturing, all right here. Now, it's a planetary gear system, which is sort of like the differential in your car. There's an outer ring, there's an inner ring, and then gears that move. And so it's a way of changing speeds, because if there's an arm connected to these three outer gears, it spins at one angular rotation, and the arm connected to the inner gear spins at another. You can actually do some very interesting design things with this kind of setup. But because it can be prototyped like this, you could take this and put it in a real design and see if things are going to fit, see if they're going to move correctly. Since it's really layers of paper, you're certainly not going to use it in your car, but you can certainly try out your design and make sure it's going to work. This is something called the Riemann zeta function. This was a request we got from Professor Larry Carter from the computer science department here. The Riemann zeta function is a function of complex numbers, imaginary numbers, and it's one of the last unproven theorems in mathematics. This is what it generates. Along this line, all those curves dip down to zero. And everybody who studies this knows that that's true, but no one's found a way to prove it. And there are a lot of things people do with this function. This serves purposes even as far afield as cryptography. And everybody who uses it starts out their own work with, if we assume that all the zeros lie along this line, then the following else will happen or will be true. And so Larry Carter wanted to sort of verify that in his own mind. So he generated the data on the Mathematica program and then sent over the triangle system to us. We added the sides and the base and so on and manufactured it. There are other rapid prototyping technologies that build things a layer at a time or a drop at a time, but I don't think their models look quite as good. They make it out of layers of plastic or rosin or drops of plastic, and I think those models look much more sterile. I like the look and feel of wood, and that's what this ends up being, especially once you lacquer it when you're done, because I wanted people to feel like they wanted to pick these up and look at them and hold them. If you stick one of these out on the table and a group of people walk by, they stop and they pick it up. They sort of can't help themselves. It just invites them to do that. I'm not sure I would call it sculpture because it really is a visualization. It's almost no different than drawing something on the computer screen. In screen-based graphics, we do hard copy by sending things to a color printer. This is really just another hard copy device. And so I have a hard time calling it sculpture. It really is hard copy, but I think it's more appealing to most people than just a flat hard copy would be. The biggest satisfaction is sort of what the San Diego Supercomputer Center is about, is you ask almost anybody who works here why they like working here, and the answer is almost always the same, is we love helping great scientific things happen. The people we collaborate with, the people who take advantage of what SDSC has to offer, go on and discover great things. And when somebody here helps them do that by supplying a tool or a model or helping them get their program running on a fast computer, it's very gratifying for all of us. So when people make discoveries, when people plug two molecules together and say, oh, so that's how they go together, that's just great. That's what this place is all about.
Each year, undergraduate students from the University of California at San Diego participate in a special program to introduce elementary school students to the possibilities in the world of engineering and higher education, in a program that uses the excitement of learning to inspire youngsters to aim high.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1.
Well, what UCSD and other schools are doing is they're looking out and they're looking for the future engineers, and they just don't see them. They don't see enough students who are in math and science tracks pointing at universities, pointing at engineering. And so they need to, in order to ensure that we continue to develop the processes, the products, the goods and services that keep society moving forward, they need to actively develop interest in this major. And it starts early because preparation, the math sequences start early. So UC San Diego is doing what is necessary in order to ensure that all of us have engineers in place for the next generation. SPEED program, or Student Partners in Engineering Education and Development, was started to address a need, and that need is to get this kind of information about math and science and what students can use it for in their careers, get it out there into the elementary schools as early as possible. Our engineering students have agreed to help us get this information out to the schools by going out and doing projects and working with the students for extended periods of time. The rocket launch is the culmination of this year's visits to the classroom. They've done several activities over the past quarter, and some of those activities led to this rocket launch. In the classroom, they began to learn about aerodynamics and flight as they assembled and painted their rockets. And they brought them out here today to launch them and see for themselves the principles in action.
We targeted 4th, 5th, and 6th graders specifically because Glenda Davis, our director, and I sat back and we evaluated some of the concepts. And we fully intend to target junior highs eventually, but statistics dictate that children are making the decisions to go into gangs or be involved with adverse activities and very detrimental activities when they reach high school and junior high level. And so the purpose of us targeting 4th, 5th, and 6th grade is that we feel that they're advanced enough to understand the concepts, but we're hitting them early enough before they've made those adverse decisions. We're all here to launch rockets today, but the most important thing is that we launch them safely. Now, when you come up with your rockets, you already have everything set up. The college students that you see out here are going to be helping you put the engines in the rockets, okay? Okay. This is one of the big rockets that we're going to launch for you at the very end, but we're going to use this to show you how to properly do this. Safety is very, very important. Okay, once you put the engine inside the rocket, it's going to sit on top of the launch pad. This right here is the key. If the key is here and it's not in the launcher, then the rocket will not shoot off. Okay, this is very important for safety because when you plug in the engine, you don't want the engine to start off. Okay, now once the engine is plugged in, you remove the key and you walk back with the college student to the launcher, and then you wait patiently. All kids have to have their rockets hooked up and they have to be waiting before we can do any launches.
Jose P. Not coming. Right there. Stacy. Carlos. Sandra. Matt.
Wad it up in there, and then we're gonna roll up the parachute. So once I get it in, you don't want to take it out again. Then we want to make sure that we get it set and it'll open once you fire it, and it'll go really far.
Well, the UCSD students that are involved are from a very diverse background, both ethnically and their majors. And that was very intentional as well, in that we wanted the students to go into the classrooms, even if they didn't know very distinctly about the concepts were basic enough that they could teach them. And so we get biology students and electrical students and engineering students and computer students and all different backgrounds to go in there and show the kids hi, I'm an electrical engineering student, but I can teach you about mechanical principles and it's fun.
At some schools, engineering, you can just get stuck into the studying and go to the library and go home and sleep and go to the library. And there's more to engineering than just that. There's getting out and working on design projects, and there's also getting out to the community and really show them engineering is not something that's far away that you can't achieve. It's really realistic. It describes how things work in the real world, and it's really something that science is kind of is starting to be pushed a little now, but really kids were very tentative to go towards that way because of the math and the physics. So I just see this a chance to me to get out and help these kids and show them that there is higher education that's fun and that'll describe how things work in the real world. And I love to see the kids really enjoy with all this stuff, because this is the first step. And as my childhood, I built these model rockets and I built remote control cars, and it's just kind of the process that leads to engineering.
Students tend to gravitate to what they see, what seems real to them. And through the media, they've come to recognize medicine and business as real, exciting, stimulating, challenging careers, even though some of the programming is a little slanted towards something that's not quite real. On the other hand, engineering over the past 20, 30 years has become so slick and sophisticated, we've become so very good at what we do, that it's very hard to see what it is that we did anymore. So students see products, but they have no idea how these products came to be. Activities like this allow us to connect the students back with the products and the engineering and the math and science that went into it, so that they begin to see that by knowing math and science and by using these tools, they can design these products. Once they appreciate how they can make the products that they love, then it becomes real and it becomes something that is feasible, is doable, and something that they can actually plan for.
It's all about bringing the science and engineering principles in the classroom work and the more difficult concepts and having them culminate into something fun for the kids. And that's the whole purpose, is if it's not fun for the kids, then we may not be able to give them that extra encouragement. We want them to come to a secondary education into a school and stay away from gangs and drugs and things like that. And these kids may not have that exposure at home if their parents hadn't gone to college or if they're in a different environment or something like that. So we're trying to nurture these secondary education principles, and this is the way we're doing it. I came into mechanical engineering because there's so many different things that I can build. I want to learn how to build things like rockets, or build the parts that will allow their computers to run, or to manufacture their computers. And so that's why I became a mechanical engineer, because I can do so many jobs. And every company in the United States somehow needs a mechanical engineer to do something. Even if they only have to build the tools that they work with, everybody needs mechanical engineers. And so that's why I became a mechanical engineer. And also, no one in my family ever went to college. I've been tutoring elementary school children since I was in the military in Chicago, and I knew how rewarding it would be, and I'm very enthusiastic about community-oriented events. I think that it's very important to touch base with the children, because the children are the ones that are going to make the difference with engineering in society in the future. And so if we don't reach the children and help them with these difficult decisions and guide them in the right direction, then our future is in trouble. And so it's a personal conviction that I've had since I was a teenager.
Each of you will receive a certificate today for participating in UCSD's rocket launch. You're also going to receive a coupon for McDonald's, and you're going to receive a special pencil that says UCSD on it, and a really good lollipop that has chocolate inside. Each of your teachers is going to get a can of silly string. How about that?
get personal satisfaction from several aspects of this activity. First and foremost, I see little kids coming out and looking at math and science, and hopefully many of them are realizing that it's not for the chosen few. It's for whoever wants to do it and is willing to make the sacrifices necessary to be good at this. And they'll begin to start asking more questions and talking to more people who can help them do this. So in a way, we've turned on the light bulb for some of these students today. I also get a great amount of pleasure in watching the engineering students learn to help others embrace and appreciate this major and what goes on in this major. They're having a great time. They're teaching others. They're working together as team members in ways that they've never done before, and they're liking it. And when you get that kind of energy and enthusiasm running through the School of Engineering, you can begin to do a lot more for the student body in the School of Engineering. They begin to want this, they're receptive to it, and they're willing to work with you to help get it. And so I'm in a win-win-win situation as far as working in these activities. I can see the future engineers coming, and I can see the engineers I have developing the skills they need, that they will need when they go out into the real world, wherever they go.
Every summer, a handful of undergraduates from around the world are invited to sunny La Jolla to participate in an annual summer session to study exobiology. Under the guidance of the foremost experts in the field, the students spend the summer conducting research in this new and exciting realm of science. We caught up with one class on the last day of their symposium to capture their reflections on the program.
What is exobiology? Well, in a simplistic statement, I think it's how life evolved on Earth and also how it may have evolved on other planets in the solar system.
Well, I think exobiology is, in a sense, kind of a deceiving label because it really pertains to the study of biology, chemistry, and physics, and combines these studies for the study of where life came from or how life developed. So constantly, chemistry, physics, and biology are being applied in this research.
I saw in television the famous TV series of Carl Sagan, Cosmos, and I was very delighted, and I thought that that was my field, and so I pursued that work, and hopefully I can join the AMSCORD people and work together on one of the most important and exciting fields of science.
I became interested in exobiology and especially the origin of life my sophomore year at UCLA, where fall quarter I took a class called Major Events in the History of Life with Dr. Bill Schopf, and obviously it discusses major events in the history of life on Earth, and I became an avid fan and very interested in pursuing that and pursuing the question of the origin of life.
The project I've been working this year has been the prebiotic synthesis of precursors of biochemical monomers in conditions that may mimic the early Earth environments.
This summer I've worked in Stanley Miller's lab, and my primary interest has been in studying the carbon isotope fractionation of the products of spark discharge reactions. As a lot of people are aware of, if you've taken a bio course, Stanley Miller is known for his classic Miller-Urey experiment with a spark discharge, a spark run through a mixture of gases that produces organic material. So I've been interested in looking at the products in the light of their carbon isotope fractionation, primarily to determine what it is, and if it's significantly light, then that would have implications on the interpretation of carbon isotopes seen in the geologic record, both on Earth and in extraterrestrial systems.
Biochemical monomer is basically the building block of the proteins and nucleic acids and all the constituents of living beings on the Earth. And we think that these biochemical monomers could have been produced under conditions that prevailed in the early Earth.
I looked at Greenland and Antarctic ice cores and examined them for amino acid content to try to get an idea of how many of these amino acids are coming from the Earth, and possibly, if any, are coming from Mars, coming from other places.
Well, this summer I was involved with studying the sublimation of amino acids at high temperatures. What we wanted to try to do is model the atmospheric entry of meteorites and see how amino acids on meteorites may behave when you enter the atmosphere and heat them up. What I brought here is the sublimation apparatus that we use to model this. And what we do is we put the amino acids on this end and heat them up to very high temperatures, 1100 degrees Celsius. And what will happen is they'll vaporize and recondense on this cold finger, which is cooled to very low temperatures, minus 195 degrees Celsius. This temperature is similar to what you may expect in outer space. So essentially what we've done is we've modeled what happens to the amino acids when they enter the atmosphere.
Well, the reason why I'm looking at both Greenland and Antarctic ice for amino acids and for carbon is that I'm trying to get an idea of what levels of contamination there are in the ice in Antarctica. In other words, if we go and look at a meteorite, a Martian meteorite that's landed in Antarctica, we need to have an idea when we test it of what we should expect from the Earth, what's coming from the Earth. And then we can know that everything that's beyond that is possibly from other sources, possibly from Mars. So this research, the work that I've been doing, has been focused on trying to determine what do we see in this ice on a regular basis? What do we see in, that's from an earthly source of amino acids?
We have rock records on Earth, and we're potentially going to have samples from extraterrestrial locations. Carbon isotope signatures are often used to indicate life or the absence of life. At the moment, we have standards that where we judge these values by that we find in the rock record. I'm testing the validity of these standards, and perhaps might find in the big picture that carbon isotopes should be viewed with caution and interpreted cautiously when seen in our rock record and extraterrestrial samples as well.
We know that the early Earth was plenty of chemical, organic chemicals, and what we don't know, we still don't know which were the actual molecules that were present. And the work I'm doing is to ascertain which molecules were in the prebiotic soup.
The day-to-day ins and outs, this lab, I think in particular, prebiotic chemists in general work very hard. There's a lot of late nights, a lot of nitty-gritty working with icky chemicals, mixing up chromerge to make sure my glassware isn't contaminated. Late nights, mixing up buffers, actually running a spark through a mixture of gases that contains hydrogen, hoping that the flask hasn't leaked and that I won't take out the entire third floor of the chemistry research building and everyone in it. So there's a certain element of danger and excitement, a certain element of mundane, completely undesirable chores that need to be done. It's a combination, but all in all, it's hard work that is worthwhile ultimately.
In my work, I generally have the opportunity to do many things, but there's a lot of wait time. There's a lot of evaporating down water and waiting for samples to dry out and things like that. But there's a lot of opportunity to do different testing. I get to test for amino acids using one machine, get to test for carbon using another machine. So I really learn how to use many different instruments in the lab. And it's really exciting. It's a really good learning experience.
Day-to-day might consist of I'll come in at like 8 o'clock in the morning. And you need to get the laboratory set up. So there's some maintenance things that go along, changing the oil in pumps, etc. Once that's done, then you can start doing the fun stuff, the sublimations and, mimicking meteorites entering the atmosphere and stuff like that. And that consists of the majority of the day, doing the sublimation experiments. And things may not go as planned, so you may have to work later hours to get things to go right.
I think the most exciting was probably the spark discharge, the electric discharge reactions, because number one, they are a little bit dangerous, or they're a little bit exciting, and you have to be careful and hope that everything goes well. But also, it's been my privilege to do them in the Miller lab, as there aren't that many people on the planet who have done Miller-Urey spark discharge reactions, and I'm pleased to have taken part in those in any way, shape, or form.
For me, it has been fundamental to participate in the unscored exobiology program, because in my own country, there's no research group which is working on the origins of life field. So it is very important for me to acquire the knowledge and the technical skills that I'm learning in La Jolla to translate into my laboratory in my own country in Barcelona.
I'm incredibly excited to have the opportunity to do research like this with the NSCORE program, because this is the field of study, as far as I'm concerned, that is the most up and coming right now. The study of extraterrestrial life, whether or not it exists, the philosophical and scientific questions that underlie it, are at the forefront of topics, in the news today, and that people are concerned with. And basically, it's very exciting. It's very exciting to know that the work that I'm doing might one day lead to some very astounding results.
I think the most exciting thing about what I'm doing is that nobody else has really done it. And everything I do on a daily basis is new. I can't necessarily explain what I'm seeing, and I'll have to, go through the data and really try to analyze it. But it's all new and exciting. Nobody's done this before. So I think that's the most exciting thing about my job, is stumbling upon new data and new discoveries every day.
Without a doubt, this has been a major boost and stepping stone in my scientific career, if I choose to pursue a scientific career. There's absolutely no substitute for hands-on experience and doing research of your own. There's no lab or no class in any college, I think, that comes close to having something that you want to do and answers that you want to find and having to do it.
I definitely think that this experience will enhance my career. As I said earlier, I'm from a physics background. I'm learning more of the chemistry. I'm becoming more broad in my knowledge of the various sciences. Ultimately, I'd like to become an astronaut, and they may see exobiology as something that is very important. They may be looking for exobiologists to fly on shuttle missions and go to Mars, maybe, who knows.
The effects of the research going on today, from a societal standpoint, will have a lot of impact. There's, as we've discussed, the field is growing very rapidly. It's wide open. We're going to Mars. We're getting samples from other places, and we're learning a lot about the origins of life. We haven't pushed it back to the absolute origin of life yet, but we're getting closer and closer, and it's a hot topic for debate, not only among NSCORE fellows or the scientists, but everyone in our society is pretty interested in it in one way or another, whether creationists or scientists.
It goes way beyond science. And, the science is the tool to get the answers that we're looking for, as far as the question of, is there life on other planets, or was there ever life on other planets? And so I think in today's day and age, I think that it's not going to be as much of a problem as it may have caused in the past. I think that there's a bit more of a tolerance for different views, but at the same time, it's going to create a ruckus. If we get results that say, oh, there's extraterrestrial life that, and we've proven it, it's not going to be something that's going to be taken too lightly.